Are you looking for a way to more easily integrate AWS Lambda with your favorite monitoring, observability, security, governance, and maybe other tools? Well, thank you for joining me today, where I'm going to be talking about integrating Lambda using Lambda extensions. My name's Julian Wood, and I'm a senior developer advocate here at AWS Serverless. I work with builders and developers to help them understand how best to build serverless applications, as well as being their voices internally to make sure we're building the best serverless products and features. Prior to this, I was an infrastructure engineer, architect, and manager for many years. I've worked in large global enterprises and startups in the world of finance and radio broadcasting. Please feel free to contact me anytime with your serverless questions, whether you have questions from today or other general questions around serverless development. So what am I going to be talking about today? I'm going to be talking about Lambda extensions, how they work, how you can use extensions, how extensions impact the Lambda Lifecycle, a bit about the new container image format and how that impacts packaging extensions, and then how you can use extensions to send logs to custom destinations. If we think of a traditional compute environment, it may have long-running processes, and these start when a host or a VM or a container sidecar starts up. An agent or a tool then performs some work or analysis while it is servicing various requests. And this agent or tool may run for the whole time after an instance is started or until it is shut down. Lambda invokes your function in an execution environment, which provides a secure and isolated runtime environment and manages the resources required to run your function. But if we had to have the same kind of model for Lambda, which is short-lived compute where you don't pay for idle, this would be wasteful. If you had to maintain a long-running agent process that needed to stay running with intermittent invokes, this would cost more and that would be unnecessary. And so we've released Lambda extensions, which is a new way to easily integrate Lambda with your favorite tools. Lambda extensions augment your Lambda functions and work within Lambda's shorter compute duration without having to maintain a long-running process. You can add an extension to your functions and in effect you're plugging them in, and this allows you to use existing tools and they can deeply integrate with the Lambda service to pull data out about function invocations. You use or consume the capabilities of an extension by dropping an extension into your environment and maybe adding some configuration information, and this is done via environment variables. And this gives you more flexibility in the tools you choose. It certainly simplifies your architecture and helps reduce function code. That's always a winner in my book. There are a number of use cases for extensions, and these include observability and logging and being able to capture diagnostic telemetry data. And this is not only during your function invocation, but before and after the invocations as well. You can use extensions which automatically instrument your code to get insights into how your functions are running. Or you can use extensions to fetch and cache configuration settings or other values before your functions themselves run. And hardened security agents can run as extensions to detect and alert on function activity. Extensions extend Lambda's invocation lifecycle to only run when there is something to do and not needlessly run where there isn't something to do. They can also continue to run after a function invocation has finished to send telemetry data out about the invocation. They can initialize and work before the runtime starts and can perform cleanup tasks before the execution environment is spun down. We know that you have a wide range of systems that you need to manage and may prefer to use a single commercial or open source stack to operate maybe your on-prem and also your AWS resources, rather than mix and match operation systems or to have you to use something different for serverless. So Lambda extensions is designed to support the tools you already use today to observe and operate Lambda functions. They're simple to configure and manage, and there are a number of extensions and integrations already available from our many partners, and there are more to come. There are also tools from AWS and open source that also use Lambda extensions. Extensions really makes it easy to use your favorite tools with Lambda. So let's have a look at how extensions actually work. There are three broad components of extensions. There are the extensions themselves and how you can use or consume an extension by adding them into your environment by configuring the options in your functions. The Extensions API makes it easy to build or integrate your own tools to hook into the Lambda Lifecycle. And then there's the Logs API, and this allows extensions to get logs data directly from the Lambda service, and these logs can then be sent on elsewhere. Now, each of these broad topics has a related blog post if you also want to read an overview, and as I've mentioned, I'm going to be covering a lot of these details already. You deploy extensions into your environment for zip archive functions by using whatever tool you currently use to build Lambda functions, and you add a Lambda layer to your function, and then add some configuration information via environment variables to use the capabilities of an extension. For functions deployed as container images, you include the extensions within the function image within the Docker file, and you can also create shareable extension container images. When Lambda then starts up the execution environment for each Lambda function, it searches the /opt extensions directory and starts any extensions found, and the extensions do need to be executable for this to work. A simple way to show Lambda extensions in action is to just look on a normal Lambda function. I have a function here, I have no Lambda layers, but if I was to go down and select one of the advanced monitoring tools and enable advanced monitoring, this tells me it's going to use CloudWatch Lambda Insights. And Lambda Insights actually under the hood uses Lambda extensions to gather some advanced telemetry data about function invocations. So once I have that done, if I then go and look at the Lambda function, I can see that a Lambda layer has been added, and this has been added as the Lambda Insights extension using the version on. So I'm now consuming the capabilities of an extension without even realize I'm using an extension. And you can think of this as how a tool would be able to plug into Lambda and just be able to add itself to your functions and be able to gather telemetry data. If I was, for this example, going to then test this function and run a number of invocations, if I was then to head over to CloudWatch and to the performance monitoring part under Lambda Insights, I would be able to see the CPU usage and the network usage, which is something that the Lambda Insights Lambda extension is able to give me. So this is an example of using an extension, and just behind the scenes, Lambda Insights is using Lambda extensions to provide the functionality. Lambda supports two types of extensions, internal and external extensions. Internal extensions run in process with your code as separate threads, but still within the runtime process. External extensions run as completely separate processes, but still within the same execution environment as the Lambda function. Internal extensions allow you to modify the startup of the runtime process and run additional scripts. As I said, they run in process with your code as separate threads, but still within the single runtime process. And the runtime process controls the lifecycle and stops and starts the extensions. The two flavors of internal extensions: language-specific environment variables and wrapper scripts. Language-specific environment variables are set as part of the function configuration. You set your function environment variables for various runtimes. Java tools options, for example, is a variable you can set for Java, Corretto 8 and 11, and you use the variable to specify additional command line parameters. You can specify the initialization of tools, specifically the launching of native or Java, in this case, programming language agents using the agentlib or Java agent options. Node_options is supported for Node.js 10 and above, and .NET Startup hooks is supported for .NET Core 3.1 and above, and this specifies a path to an assembly DLL that Lambda can use. So just looking at the example here, you would set Java tools options to use the -java agent command line argument when the runtime starts Java, and this will then preload an example agent.jar file. And you don't need to modify your code to add the agent, and in this way, internal extensions can also be used to auto-instrument your code. And using language-specific environment variables is a preferred way to set up startup properties. Let me show you how to configure the environment variable. I have a Java function configured here. It's a very simple hello world function, which doesn't do much. If I invoke the function, all it's going to do is respond with the body, not much information. Now, what I can do is I can go into the Lambda function environment variables, which is further down over here, and I can add an environment variable for the Java tools options. Now, as I mentioned in the previous slide, I could put a dash example jar file using the dash Java agent value. And this would be, for example, if I had an agent I wanted to add to the Lambda function. So you would package up example agent as a jar file and then deploy it as a layer or include it with the function code. And then the JVM will try to locate the class in example agent and invoke its pre-main method before the application's entry point. But what I'm actually going to do is I'm going to do something slightly different and actually show an entirely codeless solution for this. And this is an example of using Java Tools options with dash verbose colon class. And this is a Java Tools option setting to track the loaded classes and their locations. And you can use this, for example, for troubleshooting when you maybe don't know which version of a library is being used and when the first one in the class path isn't the one used by the applications. And so it's a troubleshooting step that you could just set this environment variable. So I save that environment variable, which is going to take a short amount of time. And then I'm just going to invoke the Lambda function again. So now what's going to happen is when the Java process starts, the JVM is going to start with a dash verbose colon class, and the function execution result is going to be in the same. But looking at the log output now, I can now see all of the classes that have been loaded. So that's got the classes and their locations, and this can help me troubleshoot and understand exactly what's loading when my function invokes. So I can use the Java Tools options with specifically Java for a number of different ways to help me with my serverless application. You can create a wrapper script to customize the runtime startup behavior of your function as well, which allows you to set configuration parameters that can't be set through language-specific environment variables. So when you use a wrapper script, Lambda delegates the runtime startup to your script. It sends the path to the interpreter and then all the original arguments. What your script can do is then change the startup behavior of the program. For example, the script can inject and alter arguments, it can set environment variables, maybe capture some diagnostic information or some errors. And the way you specify the script is by setting the value of the AWS Lambda exec wrapper environment variable, and you set this to the file system path of an executable binary or script. To show how a wrapper script works, I have a Python example function, which I'm going to configure a wrapper script for. If I do a test invocation for this Python function, it really doesn't do nothing. All it's doing is doing a hello from Lambda. And if I look in the CloudWatch logs groups for the function invocation, it is just outputting the event that it receives for the invocation. What I can then do is go again into the environment variables, and I can go down and I can configure the environment variable for the AWS Lambda exec wrapper, and I'm going to point that to a wrapper script, and this is going to be a file I'm going to add within the Lambda function folder. So once the environment variable has saved, I can go down, and once the function code has loaded, I can see I have the function code, which is just doing the hello from Lambda, but this is the wrapper script I want the function to run. And what this is going to do is this is going to launch the Python 3 and add the extra arguments, which is going to be the -x import time option. And it's going to start the Python interpreter with this additional option. And then when you run the function, Lambda is going to generate a log entry to show the duration of the import time for each input. So I'm wrapping the Lambda function with another script to launch Python with this extra argument. So once that function environment variable has been saved, which I have it over there, if I then go and do another test invocation of the Lambda function, and I go to CloudWatch logs and I look at the most recent log stream when it pops up and has been delivered from the Lambda function, this is going to show me a lot more information. So I'm just waiting for the log stream to appear, and I select the log stream, and what I can see as it appears is here is all the input time information, which is far more information than I had before in the different log entry, and it's showing the duration of the import time for each of those imports. So what I've done is just by configuring the environment variable settings in a Lambda function and launching another wrapper script, Python has been able to launch with another new import time option. And external extension runs as an independent process, and this is separate from the runtime within the execution environment. You can see the process boundaries here. It can start before the runtime process and continues to run after the function invoke is fully processed. Because external extensions run as their own processes, you can write them in a different language than the function. And this is best done if it's a self-contained compiled binary that is compatible with all of the supported runtimes. To show some more external extensions functionality, I have a great demo which works with AWS App Config. If you're not aware, App Config is a systems manager feature that allows you to deploy configuration settings to infrastructure, including Lambda. What makes App Config super useful is being able to carefully introduce changes to your application that can be only tested with production traffic, and it's got robust deployment and testing capabilities to make sure the new configuration changes are deployed safely. The App Config extension runs as a separate local web process, and this caches configuration data from App Config and makes it available to the function. The function then makes a local HTTP call. It retrieves the latest App Config setting from this extension, and because it's local, it makes it super fast and doesn't require any App Config CLI command within the function. And you configure which App Config setting to retrieve as a Lambda environment variable. Here's the link to the GitHub repository, which includes a number of extension demos. If you browse AWS samples and then to AWS Lambda extensions, you will find the App Config demo extension, which is deployed using AWS SAM, our serverless infrastructure as code tool. Jumping to VS Code, you can see there's an application which deploys all the components, and this is stored in a SAM template. This consists of a Lambda function, and this runs Node.js, and it has a Lambda layer added, which is the app config publicly available on, which is stored in the template as a configuration parameter. A SAM deploy then deploys all the infrastructure for the application, which I've run through already to save some time for the demo, although it doesn't really take long. We can see various app config things deployed, as well as a Lambda function and associated IAM roles. So jumping to the deployed app config configuration. This is where you can configure a number of app config features for doing those safe deployments. Here you can see there is what's called a hosted configuration version, and I've used this to store a log level value of normal, and you can see that within the content. Now, jumping onto my Lambda function code, this returns the event, whether it's a cold start and the log level value from app config. The function has an environment variable, which is configured here, which specifies that we want to use the app config log level configuration setting. The extension has access to the same environment variables as the function. We can see the Lambda function has a Lambda layer configured. This was added during the SAM deploy and uses the app config publicly shared layer on. Now, remember the function code is going to make a local HTTP call to receive the app config configuration. There's no AWS SDK or CLI installed. It's making a local call, which we can see here, which is fast. The extension behind the scenes is caching the information from app config. If I then do a test function invocation, which I set up here, I could also test this locally using SAM. Once the function is run, we can see here that the log level return from app config is what we saw in the app config console as normal, and the cold start value is set to true. If I run the function again, we see the same value returned from app config extension, but now the function cold start is false. It's doing a warm start. Heading back to the app config console, I create a new hosted configuration version and I change the log level to verbose. Once that is created, I then go about deploying the change. I could use many features of app config to test the rollout of this deployment, either using tested Lambda functions or various deployment strategies. I'm going to keep it simpler and deploy the change immediately. So I can watch the deployment status until my deployment of the new version with verbose logging is complete, and as the function currently deployed version is version number 2, which you can see over here. So heading back to the Lambda console, I run another test invoke. I can now see that the log level has been updated to verbose. The extension has seamlessly cached the updated config. But also note the cold start is still false. This is a warm start. I've deployed a configuration change to a Lambda function without having to update the function with an environment variable and redeploy the function. For a single function, it would be very easy, but think how you can use this to update hundreds of functions with a config change, maybe based on a metric you're picking up, and not have to redeploy. The next invocation, even a warm start, gets the updated configuration from the Lambda extension. So you saw how the Lambda extension communicated with the external app config service, providing a handy outer function code mechanism to synchronize the data with the external service. Lambda uses a local HTTP GET to retrieve the configuration, which is simple and fast. Time now to look at resources and security and how extensions work with your Lambda functions. As extensions run in the same execution environment as the Lambda function, they share resources with the function, such as CPU, memory, and temp disk storage. Extensions also need to be compatible with the associated operating system, and if an extension needs any, say, network access, for example, you must apply network egress rules to the function configuration. In addition, extensions share the same IAM role and security context as the function. So the extension has access to everything the function has access to, and if the extensions need access to something, this must be included in the function IAM role. You can include up to 10 extensions per function. These can be packaged in up to 5 Lambda layers for zip archive functions, and in this way you can actually package multiple extensions within a single Lambda layer. For container image functions, you build and include the extensions files within the container image. The size of your function's extensions counts towards the deployment package size limit. For a zip file archive, the total size of the function and all extensions can't exceed the unzipped deployment package size limit of 250 meg. And for a container image, this is much larger. This is 10 gig. And looking at performance, there are a few things to bear in mind with extensions. Extensions may impact the performance of your function because they do share resources such as the CPU, memory, and storage with the function. And because extensions are initialized before the function code. For example, if an extension performs some compute-intensive operations, you may see your function's execution duration increase because the extension and the function code share the same CPU resources. It's also worth remembering that because Lambda allocates proportional CPU power based on the memory setting, your function may see increased execution and initialized duration if your memory is set at a lower setting, as more processors are competing for the same CPU resources. What you can do to impact this is actually add more memory to a function, which then also proportionally increases the CPU and network throughput. One thing that has changed in respect to a performance improvement with the general availability of the extensions is the response from the function is decoupled from the response from the extension. The response from the function happens before the extension finishes, and this speeds up function response times while still allowing extensions to carry on their processing. And also from a timeout perspective, functions and all extensions must complete within the function's configured timeout. To measure the extra time that the extension takes after the function invocation, you can use the new post-runtime extensions duration function metric. And you can also use the CloudWatch duration and max memory use metrics to measure the overall increase in time and memory used. And to understand the impact of a specific extension, you can run different versions of your functions side by side with and without the specific extension and work out the impact. For pricing, extensions share the same billing model as Lambda. You pay for the same number of requests served and the combined compute time. So this is the total time that the function and all extensions run for. There's no separate pricing dynamic for Lambda extensions. And this is measured in 1 millisecond granularity. So let's look now at the changes to the Lambda lifecycle and how extensions running your tools can integrate deeply into the Lambda service. Before extensions, there was only the Runtime API, and this provides an HTTP API for newer, managed, as well as custom runtimes to receive invocation events from Lambda. This is how functions receive events from the Lambda service and how they return function responses back to Lambda. The Runtime API is what enables you to bring the custom runtimes to Lambda. Before extensions, there were only two parts to control the execution environment with Lambda: the runtime and the function. I'm going to go through the timeline of how the runtime and function interact, which runs from left to right. Lambda initializes the runtime, which then runs the function initialization code, which is the code outside the handler. This is the cold start. During an invocation, the runtime manages the function invocation and the function handler code runs. The runtime handles the communication between Lambda and the function. When the invocation finishes, Lambda freezes the execution environment so you don't pay for idle. When the next invoke comes in, Lambda unfreezes and reuses the execution environment for a warm start, and the runtime and function do their work. When there are no pending invocations or Lambda refreshes the environment, Lambda then removes the execution environment. With extensions, we're introducing the Extensions API, which builds on the existing Runtime API. Extension authors use the Extensions API to register for function and execution environment lifecycle events, such as Invoke and Shutdown. In response to these events, extensions can start new processes or run logic. Extensions can also use the Logs API to register for and receive logs directly from Lambda without having to go via CloudWatch Logs. So let's take a look at what this looks like with a timeline. We can see here how the init phase of the Lambda lifecycle is enhanced. When setting up the execution environment, Lambda searches the opt extensions folder, finds any extensions, and runs them as separate processes. The extension files need to be executable for Lambda to run them, and if not, you will get an access denied message. And this happens before the runtime starts. An extension initializes and can do some setup tasks. It registers with the Extensions API to tell Lambda what events it wants to receive. It then completes other setup tasks, such as with the app-config example, running a local HTTP server and caching configuration settings. For an observability extension, this could be registering with the observability platform and starting to gather telemetry data. A log extension, which would start its log streaming receiver. Then the runtime process starts, initializes the function to run the code outside of the handler. And you can see Lambda manages the runtime process. You then manage the code and configuration of extensions as well as your functions as part of the function configuration. Then the function invokes. The extensions continue processing. Lambda freezes the execution environment when all extensions signal they have finished processing and unfreeze when a new invocation comes in for a warm start. You can see the extensions can do some processing after the invocation to, for example, process telemetry about the particular invocation. If there are no pending further invokes or Lambda refreshes the execution environment as part of managing the servers, the runtime shuts down. And then the extension has time to run final tasks before the execution environment is removed. And this could be to send out any remaining logs or telemetry data, or notify or maybe close some connections to any other systems. So you can see Lambda is exposing more of the function lifecycle with three distinct phases: init, invoke, and shutdown, which extensions can tap into to allow your tools more visibility and control of the Lambda lifecycle. Having a look now at Lambda billing. Extensions share the same billing model as Lambda. For invokes, you pay for the number of requests served and the combined compute time in 1 millisecond increments, as I mentioned earlier. And this is the total time that the function and all extensions run. For shutdown, there's no request, you just pay for the build duration. So let's take a look now at some of the extra information if you were to build your own Lambda extensions for something to integrate your own custom tooling. Here's the Runtime API endpoint, which newer managed runtimes as well as custom runtimes call to get function invocation events from Lambda and send back their responses. AWS Lambda Runtime API is an environment variable Lambda makes available pointing to the address. And you can see the API path is /2018-06-01, which is the Runtime API version, and then the path /runtime. Extension authors who want to write their own tools use the new Extensions API to integrate deeply with Lambda. This is how extensions communicate with Lambda to receive information about function invocations. The Extensions API uses the same Runtime API environment variable, but as you can see here, extensions communicate with the Extensions API path /2020-0101 as the version and then the path /extension. Lambda extensions can also use the Logs API to receive logs directly from Lambda, and I'll cover this in more detail shortly. The Lambda documentation, which I've linked to here, has a handy flow diagram for the different phases in it here, which goes through how the three components, extension, runtime, and function communicate during init. And you read it by going from top to bottom and following the arrows to see the communication flows. For the invoke phase, the Lambda docs also show the flow for each invocation, and this is obviously repeated for each warm start. And you can specifically see here how the runtime responds back to Lambda before the external extensions sends its response. And this is the performance improvement I was explaining earlier. Just to explain duration using this diagram, when a Lambda function invokes, its overall duration is the total amount of time that your function code spends processing an event. To know the performance impact of extensions on the invoke phase, Lambda outputs the post-runtime execution duration metric, and this measures the time spent between the runtime's API request and the last extension's API request. And that's the extra time extensions take over and above the runtime. To measure the increase in memory used, you can use the max memory used metric and run different versions of a function side by side to understand the impact of a specific extension. And again, you can see the shutdown phase flow diagram in the documentation. This is a great quick demo to get started, but can teach you loads about Lambda and about extensions. It's a custom runtime extension demo on the GitHub repository. What this does is it's all deployed via AWS SAM, and it's using a custom runtime using AL2, and it has a custom runtime layer and an extensions layer. And it's basically built by using Bash, and it's got the runtime, which echoes a whole bunch of information to show exactly what the runtime is doing. The function file echoes exactly what the function is doing, and the extension files also echo exactly what the extensions are doing. And what I can do here even from within VS Code, I can execute this function using any invocation, and that is going to invoke my function. What I can then do is I can go into CloudWatch logs, again from VS Code or from the AWS Management Console, and I can see in glorious detail everything that's going on that's being logged. So I can see here I've got information from the runtime that's logging, from the function that's logging, from the extensions that's logging. You see the cold starts, you see the warm starts, you see the values that are being passed around. And this is a really good way to learn all about Lambda and Lambda extensions and follow the log lines. So with the option to package Lambda functions as container images, how do extensions fit in? Lambda container image support allows you to build and package your functions as container images from a Docker file. And this means you can take advantage of the rich container tooling ecosystem, including the Docker CLI. If you use container tooling to build applications, this allows you to benefit from the simplicity and familiarity of container development practices and dependency management, but also get the operational benefits of Lambda, with a larger deployment package size of up to 10 gig compared to zip archives, which are 250 meg. So you still enjoy Lambda's automatic scaling, high availability, start times of typically tens of milliseconds instead of seconds, and native integrations with 140 AWS services, and only for paying for what you use. Extensions are deployed to zip archive functions as Lambda layers. And Lambda layers are not directly supported in container image functions, as images are created at the build time. Remember, layers and extensions in zip archives are just files copied into the execution environment under /opt and made available to functions. So this means you can use the Docker file to add the same functionality of layers and extensions to your function container images just by copying files. And there are a number of ways to add the files you need from layers and extensions to your container image functions. An extension publisher can have a container image format version of a Lambda layer. Instead of adding a Lambda layer, you add the container image layer to your function build process. As Lambda layers and extensions are simply files, if you have the code, you can include the extension file in the container image. And then in a two-part process, if you want to share the extension container images in a similar way to Lambda layers, you can package the layer or extension files as its own container image and then share them as you would other container images. When you then build your Lambda function, you then add these container image layers to your Lambda function as you would any other container image layer. If there's an existing Lambda layer without a corresponding container image version, you can actually extract and copy the contents of the existing Lambda layer into your function image. And you can see here a log extension image is added to a function Docker file, and then the files are copied into the /op directory, which would then have an extensions directory containing the extensions file. And there's a blog post via the QR code and link, which goes into a lot more detail on how to use the different options. So as I mentioned earlier, you can also use extensions to receive logs directly from the Lambda servers and send them onto custom destinations. Lambda automatically captures runtime logs and streams them to Amazon CloudWatch. This log stream contains the logs that your function code and extensions generate, and also the platform logs that Lambda generates as part of the function invocation. Lambda extensions can use the Runtime Logs API to subscribe to log streams directly from within Lambda's execution environment. Lambda then streams the logs to the extension, and the extension can then process, filter, and send the logs to any preferred destination. First, the extensions do need to register with the Extensions API in the normal way to receive the extension identifier, and then the extension can then subscribe to receive logs, and this is by sending a separate subscription request to the Logs API. The Logs API allows extensions to subscribe to 3 different log streams. Function logs, and that's the normal function logs that the function generates and writes to standard out or standard error. Lambda platform logs, and these are the start, end, and report line logs. And extension logs that extensions code generates. So always nice to see this in action. I have a demo of a logs extension packaged in a function as a container image. The extension runs a local HTTP endpoint to receive logs directly from Lambda. This subscribes to receive platform and function logs, but not to receive extensions logs. And this extension could be extended to maybe filter, transform, or process the logs in some way. And in this more simple demo, the logs are copied to S3. And then the logs could be stored long-term in S3 for archiving, or maybe sent onto another system for analysis or troubleshooting. Again, you can try yourself from GitHub. There are 2 versions. I'm going to show the container image deployment demo, and you can link to the repo via the QR code. I have a log extension which runs a local HTTP server, and I have the files locally for this extension which are stored, and I'm going to add it to the container image. The Python extension is going to write the logs to S3 using the put object API call. I use a Docker file to build the image for the extension, and I'm going to use the multi-stage build with a minimum Python image to copy the files from my local machine into the container image and install the Botter3 dependency using standard pip install. I then start a new base image and copy the files and dependencies to the final extension image, which again gets pushed up to ECR. I then have a simple Lambda function which returns a response to the client, and ultimately these function logs are going to be sent to S3. Looking at the Docker file to build my function, I add the previously created extension image and add the files from the image into the function container image. And further down in the Docker file, I set the Lambda handler. The function is then deployed using SAM with a package type of image and configured with an IAM role, allowing access to an S3 bucket created as part of the deployment. And there's also metadata here to say where the Docker file and function code is located. And again, I've deployed this in advance to save some time, but it really doesn't take very long if you do it yourself. So into the AWS Management Console and heading to the Elastic Container Repository, I can see that there is an image uploaded for the extension and another image uploaded for the function, which includes the files from the image. Looking now at the Lambda function, when I head into it, I can see for the Lambda function configuration that there are actually not going to be any layers added, as you can't with container images. And the function has been built using the Docker file from the function container image I previously uploaded. Here's the S3 bucket name configured as an environment variable, which the logs extension uses to know where to send the logs. So I have configured a test event, and I'm going to invoke the function a few times, and you can see on this first invocation I'm going to get a successful response. And just for fun, why don't I go and deploy or go and invoke that function just a few more times to generate some more logs. If I then head over to the S3 console, I can see the log files have arrived in S3 from the extension. The extension works seamlessly behind the scenes. The function doesn't even know logs are heading to S3. I can then go ahead and I can open the files from S3, and I can see when they open that I expect to see the platform and the function logs. Let's just zoom in and word wrap so I can see that. But I don't actually have the logs from the actual extension, as I choose not to subscribe to these. So Lambda has sent the logs directly to the extension without going to CloudWatch, and the extension has sent the logs directly onto S3. And you can use this to send logs to any custom destination. There's a lot more demo code on GitHub, which you can explore to learn more about extensions. You can look at the app config code to see how you can use an extension. The custom runtime shows how to build an extension with loads of logging to help you understand the full Lambda lifecycle. And then there are two versions of the log extensions, one for zip archive and one for container image packaging formats. And there are plenty more in other languages, including example extension wrapper scripts. And please feel free to contribute and add your own interesting examples, as this is all open source. So I've covered a lot. Hopefully it's all helped you to get a good understanding of Lambda extensions. I went through how extensions are a new way to integrate a whole set of tools with Lambda. You add them to your functions to augment the capabilities of your functions for a number of use cases. I explained the differences between internal and external extensions in detail and how you can use them, with even some demos you can try yourself. I spent time going through the updates to the Lambda Lifecycle and how you can build your own extensions using the Extensions API. I covered how you can receive logs directly from Lambda using the Logs API and send them onto your own custom destinations. And also covered how you can still use extensions in functions packaged as container images without using Lambda layers. The link and QR code takes you to a helpful landing page with everything about Lambda extensions. For plenty more information on all things serverless, we have a super aggregation site called serverlessland.com with lots of resources, blogs, videos, workshops, and learning paths. Everything about serverless on AWS. Thank you. I really appreciate you taking the time to watch today, and hope I was able to help you understand how Lambda extensions can help you do even more with serverless. My name is Julian Wood, and you can find me on Twitter at Julian_Wood.